Hello students, today we'll continue the chapter gravitation and today we'll study weight and thrust and pressure. Okay, so here already we have studied, I have to take the pen. So already we have studied mass, right? And we have denoted mass with M. Weight, that is dependent on the acceleration, gravitational acceleration. So weight is the mg. So that means the weight may vary with the acceleration. Now next topic, whatever we are going to study, that is the thrust and pressure. Thrust and pressure. So here first we are seeing here in this picture, one person you have in the earth. It has the mass 120 kg. Similar mass it has in the moon. This person, weight of this person is 120 Newton, but the weight in the moon, that is 20 Newton. That means the weight in the earth and in the moon, there is a big difference between the weight of a same object which has the mass 120 kg, or the mass is equal for all the planet or all in the moon and earth, but here you have that the weight is different. Okay, now in this figure, from this figure we may conclude that weight of an object on the moon, weight of an object on the moon, that is 1/6 of the weight of the object on the earth. So that means if the weight on the earth, let me write here, weight on the earth, suppose this is WE and weight on the moon, that is WM. So here whatever the weight in the moon and whatever the weight in the earth, this ratio will be 1/6. Now in the next slide we will do the derivation why it is 1/6. Here in this case, let me derive this thing. Just a minute. I have to change the ink color. Here, suppose a body of mass m, okay, the mass of the body is the m, and its weight on the moon is Wm, right? The mass is mass of the body of the or the object, that is m, and weight on the moon, that is Wm. So weight of object or the body on the moon, that equals to actually force with which the moon pulls. Force with which the moon pulls, right? The moon pulls. So we may write weight of the moon, that is the Wm. So we may write this is the Gm by r square, where G is the gravitational constant. Gravitational constant. M is the mass of earth. This is the mass of the object moon, and R is the, just a minute, R is the r is the distance. Okay. So this formula already we know this formula. Inversely proportional, the weight is inversely proportional to the distance square, and it is directly proportional to the product of the two masses. Okay. So here the weight of same object on the arc, that is WE. Okay. And mass of the arc is 100 times of that of the moon. Okay. Mass of the earth is 100 times of that of the moon. Already we know this thing. And radius of the moon, that is the earth, and radius of earth with respect to the moon, that is 4 into r. Okay. So weight of the object on the earth, weight of the object on the earth, that WE, that equals to 100 4r whole square. Okay. So if we find the ratio of the weight of the object in the moon to the ratio of the weight of the object in the earth, so we can write down that this one we may write down so here it will be 16 by 100 and it is approximately 1/6. Okay. So here we may write, in conclusion we may write, I'm writing here, let me change this one. Okay. So here, thus the weight on the moon, thus the weight on the moon is 1/6 the weight on the earth. Okay. So this one is very important. This derivation is very important for your examination also. So thus the weight on the moon is 1/6 of the weight on the earth. Okay. Next we have one numerical here. Let us solve this one. Let me change the ink color. So here what are the given data? First let me read this thing. An object weighs 10 Newton. When measured on the surface of the earth, what would be its weight when measured on the surface of the moon? Now here we know that the weight of object, from the previous derivation we know that weight of object on moon, that is the 1/6 of its weight on earth, right? So that means weight of the object on the moon is Wm, that we are denoting Wm. This is nothing but weight of object on moon. and WE, that is the weight of object on earth. So WM, that equals to this divided by 6, WE divided by 6, and here it has been given how much? 10 Newton. So 10 by 6, this much Newton. So that means we can write down the weight of object on the surface of the moon would be equal to 1.67 Newton, as this will be 1.67 Newton. Okay, done. Next is the thrust. So here, what do you mean by thrust? Here, we may notice that whenever we are just going to dip any block in any water pot, suppose this is filled with the water, and any object you have, stone, it may be block of wood or whatever, just you press this thing inside this water, you are just trying to dip this one. At that time you can see that you will feel some force against your position, against the position of the object. So this is actually the thrust. So here we know that whenever some object you have that is submerged in water, then the weight we are feeling, this is less amount. Whenever some person is swimming, at that time he will feel that his weight has been reduced. Why this happens? Because any fluids that applies an upward force on a body that submerging it, it is not only for the man, it may be if you are throwing any block, if you are throwing any wooden paste, if you are throwing any iron ball, at that time also there will be some upward force. There will be some, this is the upward force. There will be some upward force that will be acted on the body. And this is called a thrust. So the force that is opposite to the gravity, that is the thrust. Because whenever someone is just, you are just dropping any ball, iron ball, that means it will move towards the gravity. So you can feel, or the ball will feel some force against the gravity, or that means this is the thrust. So thrust is in the opposite direction of the force gravity, and it reduces the total force acting downward due to the gravity of the object. That's why the swimmer, he or she can feel that his or weight or her weight is less here. Okay, whenever they are swimming, okay. So what is thrust? This is clear. Thrust means whenever you are just dipping any object inside this water, so the object is submerged here. At that time you can see that another force will be acted upward. Always there is a force that will be acting upward, upward direction. So this is called the thrust. This one is called the thrust. Okay, and it reduces the, it feels that it reduces the weight of the object. So now the pressure. Pressure here, that is defined as the force per unit area, and where F is the surface area, pressure P, and here you have force is the pressure divided by the surface area, and the unit of this pressure, that is the Pascal. So here force F is the force acting on object, P is the pressure, and A is the surface area. Okay, and the unit is Pascal. Pressure, the unit of the pressure that is represented by Pascal. Now here you can see that whenever you are blowing that balloon, at that time it becomes harder to blow the balloon whenever it is bigger and bigger. So because whenever you are just blowing this balloon, that means what you are doing actually, you are just adding some air pressure inside the balloon here. So there will be some pressure acting in from this direction. Already the atmospheric pressure is also acting in this direction. That's why this atmospheric pressure, it resists the movement of this wall. Okay, the movement of this surface wall of the balloon. So that's why here you can see that it becomes harder to blow the balloon as it becomes bigger and bigger. Here you can see that I have told you, if some ball inside this water, you are just throwing this thing, at that time you can see that the fluid, the pressure in this fluid, the pressure is always perpendicular to the surface of an object. Here this is an object and you are just dipping this object inside the water body. So here you can see that whatever the pressure you have, these are the pressure, whatever the pressure you have, those pressures are acting just perpendicular to the surface of the body, perpendicular to the surface of the body. So it is very, very important. So it is perpendicular to the surface of the body. The pressure that is perpendicular to the surface of the body. Because whenever you have this block here, the fluid also, where you are dipping this block, at that time the fluid also, it will act some pressure on the surface of the body and it is perpendicular. So it is the pressure that is applied on an object that is submerged in water, that is called the thrust. Already in the slide, that thrust, we have given you the idea regarding the thrust. Thrust is what, whenever you are dipping any object here, at that time you can see that this will move towards the gravity, but this object will feel one force that is against its position and upward direction. Some pressure it will feel against its position. So here this is in this direction. Okay, in this direction, and this is the thrust. Okay, this is the thrust force. Now the pressure, that is the thrust divided by area. That means per unit surface area, how much thrust has been applied, that is the pressure. So if you represent the pressure unit as a Pascal, so we can define the Pascal in such a way that we have the surface area 1 meter square. We have the surface area, let me take the pen. So we have the surface area 1 meter square. Okay, and we have the thrust. Thrust is the force. So what will be the unit of this? That is the Newton, right? So we are applying 1 Newton of the force to the surface area, that is 1 meter square. So at that time, whatever the pressure you can get, or the object will feel, that is the pressure is the 1 Pascal. Okay, clear the definition of the Pascal? You have the surface area, that is 1 meter square. That object will feel a force, thrust force, that is 1 Newton. So at that time we will get that pressure is the 1 Pascal. So if pressure is the equals to thrust into area, that means the thrust, just a minute. So the thrust, from this equation we can get thrust is the pressure into area. Okay, you have to remember this. Or if you can understand this, then there will be no need to remember this. So thrust is the pressure into area. So this pressure that produces the thrust on the object, and some object, whenever it will float in water or it will submerge, that depends on the how much pressure you have. Okay, or how much is the thrust and how much is the weight of the object. So here Pascal's law, here you this arrangement you just see, one column we have, the diameter of the column is very less with respect to the column B. So here the column B is filled with water, column A that is also filled with water. One piston we are applying that blocks the A and B. Okay, so there are piston that has blocked the ends of each block A and B. So this is the piston. This is the piston. Okay. Now, if piston A is pressed, what will happen? At that time, if I press this one, then you can see that press this one means what? It will go downward. At that time, you can see that the piston B will rise upward. So we have applied the Pascal's law in our fluid pressure. So the Pascal's law we'll study. Before that, you just clear about this picture. So that means whenever I am applying some pressure on the piston of A, at that time you can see that the piston will move downward. And here, this piston will move upward. This piston will move upward. At that time, if I roughly draw this diagram, you can see that the piston is here. The piston is here and the piston A that will be here. The piston A that will be here and piston B that will be here, right? Previously in this figure, what happened? Piston A at the higher position, then the B. Now after pressing, piston A at the lower position, then the B. Okay. So what is the Pascal's law? The external static pressure applied on a confined liquid is distributed or transmitted evenly throughout the liquid in all directions. Okay. So in the previous picture also, you can see that whatever the pressure you have applied, let me draw it again. Okay, so here piston A and here piston B. Here piston B. So here the external static pressure, I have applied some pressure to the piston A. So here applied pressure, whenever we are applying with a confined liquid, here whatever the liquid you have, just a minute. This is, suppose you have water here. So whatever the liquid you have inside this arrangement, that is the confined liquid, and it is distributed or transmitted evenly throughout the liquid in all directions. Whatever the pressure you have given to this piston A, that pressure has been distributed throughout this water, confined water or confined liquid in all directions, right? The static pressure acts as at right angles to any surface in contact with the fluid. And Pascal also found that the pressure at a point for a static fluid would be the same across all planes passing through that point in that fluid. So Pascal's law, that is also known as Pascal's principle, or principle of transmission of fluid pressure. And in the year 1653, Pascal law was stated by French mathematician Blaise Pascal. Okay? So this is the Pascal's law. That means whenever I am applying some external static pressure, this P pressure, then to a confined liquid, at that time it will be distributed and transmitted evenly throughout the liquid in all directions. Okay. So this is Pascal's law. Force equals to pressure into the cross-sectional area. Okay. So force F is the force here. Just a minute. F, that is the force applied. P, that is the pressure transmitted. And what, according to Pascal's law, the pressure will be transmitted equally or evenly to all part of the contained fluid. And A, that is the cross-sectional area. Okay, cross-sectional area. Just a minute. Cross-sectional area. Now, here in this numerical, it has been stated that here they have given a pressure of 2000 Pascal that is transmitted throughout a liquid column due to a force being applied on a piston. Fine. If the piston has an area 0.1 meter square, then what force is applied? So let's solve this problem. Here, pressure given data we are writing first 2000 Pascal and area of piston that is 0.1 meter square. Fine. And we know that according to Pascal's law, F equals to PA. So here F equals to 2000 because pressure P equals to 2000. So I can write down this is P and cross-sectional area that is A. So 2000 where P equals to 2000 Pascal and cross-sectional area that is 0.1 meter square. So 2000 into 0.1, this is 0. So this will be 200 Newton. So the answer is the applied force is 200 Newton. Okay, done this one. Now this Pascal's law, we have several use in our daily life. That is, first is the hydraulic lift. Here you can see in this picture there is a car here and the weight of this car is very high amount. So here we are going to use the hydraulic lift here to move this car upward. Okay, sometimes to do any work that is mechanical work, we can use this one. Here you can see that some liquid you have in this area. That is liquid you have in this area. This is the piston B and this one is the piston A. Okay, so here it contains two pistons. Now whenever I am giving some force on the piston A, whenever I'm giving some force on the piston A, you can see that, just a minute, you can see that here this piston B will move upward. Piston B that will move upward. And in this case, you can see that you can lift any high weight object using this hydraulic lift. And whatever the force you are applying, that equals to, here you can see that A1 and A2, these are the cross-sectional area. So where A1 cross-sectional area of column A, A2 cross-sectional area of column B, and here one condition is there, A1 is less than A2. So here you can see that whatever the applied pressure, both will be same. So here if the force F1 force applied to piston A and F2, that force to piston B, here you can find that our F1 by A1 that equals to F2 by A2. Okay, that means the pressure whatever you have in the column A, that pressure equally we can feel at the piston B. Okay, so this is the main Pascal's law, and we have used in this application, that is the hydraulic lift. Now application of Pascal's law in another, find hydraulic jack or hydraulic press. Here you can see that in this object some brake pads are here and brake fluid in this side, and this is the piston. So you just see the movement of the piston and brake pads. Whenever you are making some brake here, at that time the piston that is pressing the brake fluid. So here you can see that the movement of the hydraulic jack, at that time it will be in the rest condition. So this is another application of the Pascal's law. Okay, you can see this is the belt, and I have to break the belt. That means I have to stop the belt. So when it will stop, as you can see that sometimes it is moving here. Whenever there is a pressure applied in this piston, at that time you can see that the cross-sectional area, whatever in the fluid, that will be reduced, and at that time it will be moving. This belt will move. After that time it will stop. Okay, when it will stop, you can see that the piston is moving here. So this is the hydraulic jack. Generally we are using this hydraulic jack to lift any chassis of the car, or any chassis of any very big car. Also we can use this for any other vehicles also, heavy vehicles also. So here we have another numerical. Let's solve this one. There are 3 objects and the dimensions also given. Figure shows a brick of weight 2 kgf and dimensions 20 centimeter, 10 centimeter into 5 centimeter placed in different position on the ground. Find the pressure exerted by the brick in each case. Okay, so let it be case 1, A, B and C. Fine. So let me solve for A. Here it has been given weight of brick, that is 2 kgf. So now area of base is how much? That is the 20 centimeter into 10 centimeter. That means 200 centimeter square. And pressure, that is the force divided by area, right? That means 2 kgf divided by 200 centimeter square. So we can find this pressure is the 0.01 kgf per centimeter square. Okay. Next, let me do the B. Here, area of base, that is the area of top, that is 5 centimeter into 10 centimeter, that equals to 50 centimeter square. So pressure, that equals to force divided by area. Force is already 2 kgf and area here 50 centimeter square. So it will be 0.04 kgf per centimeter square. Okay. Let's do the last one. Here, area of base, that equals to 20 centimeter into 5 centimeter, 100 centimeter square, and pressure, that equals to force divided by area. So we can find out 2 kgf, that is the force, 100 centimeter square, that means 0.02 kgf per centimeter square. Okay. So that means you have to find out the area of the base and then you have to find out the pressure. Now, one thing you remember, if it is in Newton, the weight has been given in Newton, you have to convert this dimension into the meter. This has been given in that kgf, that is the CGS unit. That's why I have not changed. So if it is in CGS unit, centimeter is okay. But until unless if they will give you in Newton, then you have to change it into the meter. 20 centimeter into 10 centimeter into 5 centimeter, whatever the dimensions, you have to convert it into meter. Next, how much thrust will be required to exert a force, exert a pressure 20,000 Pascal on an area of 1 centimeter square. Fine. Here, pressure, let it be P, that is 20,000 Pascal. Good. And area, that is 1 centimeter square. Now 1 centimeter square, that means 10 to the power minus 4 meter square. So force, that is the 20,000 Pascal into 10 to the power minus 4. So it will be 2 Newton. Fine. So you can write the answer, that is thrust is 2 Newton. Okay. Next, the moment of a force of 25 Newton about a point 2.5 Newton meter. Find the perpendicular distance of force from that point. So here, force applied, that is the 25 Newton. Now perpendicular distance from the point of rotation, that is D, so moment of force, that equals to force into D. So 2.5 Newton, that equals to 25 into D. So D is the 2.5 by 25. That equals to 1 by 10 meter. That means 10 centimeter. So find the perpendicular distance of force from that point. So perpendicular distance from the point is 10 centimeter. Fine. Thank you.